a gentle journey through the peaceful wonders of our cosmic neighborhood. The solar system moves in quiet rhythms, following patterns that have remained constant for billions of years. Each planet, moon, and celestial body follows its predictable path through space, creating a symphony of motion that continues whether we observe it or not. This exploration offers a calming look at the serene mechanics of our planetary family. The facts presented here are meant to soothe rather than startle, to invite contemplation rather than create urgency. The universe operates on timescales that dwarf human concerns, and there is something deeply restful about understanding these vast, unhurried processes. The solar system is not a place of chaos, but rather a carefully balanced system where gravity and momentum work together in harmony. As we move through these facts, the pace will remain slow and measured, allowing each concept to settle comfortably into awareness. The goal is not to overwhelm with information, but to present the cosmos as a place of order and tranquility. Mercury, the closest planet to the Sun, performs a peculiar dance that has continued for billions of years. The planet rotates exactly 3 times for every 2 orbits it makes around the Sun, a relationship called a 3-to-2 spin-orbit resonance. This mathematical precision emerged naturally from gravitational forces, settling into a stable pattern that requires no maintenance or adjustment. The phenomenon means that Mercury's day is exactly 2 Mercury years long, creating a rhythm unlike any other in the solar system. Despite being the closest planet to our star, Mercury is not the hottest planet in the solar system. Venus holds that distinction due to its thick atmosphere. Mercury's lack of substantial atmosphere means that heat escapes quickly into space during its long nights. The temperature swings on Mercury are extreme, ranging from 430 degrees Celsius during the day to minus 180 degrees Celsius at night. Yet this pattern repeats with absolute reliability, cycle after cycle, year after year. The planet's surface is covered in impact craters, each one a frozen record of ancient collisions. These craters remain largely unchanged, as Mercury has no atmosphere to erode them and no tectonic activity to reshape its surface. The largest crater, Caloris Basin, spans 1,550 kilometers across and was formed by an impact so powerful it created shock waves that traveled through the entire planet. On the opposite side of Mercury, directly across from Caloris Basin, the terrain is chaotic and jumbled, disrupted by those ancient shock waves. Mercury also possesses a global magnetic field, though it is only about 1% as strong as Earth's. This magnetic field creates a magnetosphere that interacts gently with the solar wind, deflecting charged particles in a miniature version of the process that occurs around our own planet. The core of Mercury is proportionally larger than that of any other planet, making up about 85% of the planet's radius. This iron core slowly cools over geological time, a process that will continue for billions of years into the future. Mercury's orbit is the most eccentric of all the planets, meaning it follows an elongated ellipse rather than a near circle. At its closest approach, Mercury is 46 million kilometers from the Sun, while at its farthest point, it reaches 70 million kilometers away. This variation affects the intensity of sunlight the planet receives, but the pattern remains constant and predictable. The planet completes one orbit every 88 Earth days, a swift journey that has repeated approximately 18 billion times since the solar system formed. There is something deeply calming about this constancy, this reliable repetition that requires no intervention or correction. Venus rotates more slowly than any other planet in the solar system. A single rotation takes 243 Earth days to complete, which is actually longer than Venus's orbital period of 225 Earth days. This means that a day on Venus is longer than a year on Venus, creating a temporal relationship that seems almost dreamlike in its unusual proportions. The slow rotation contributes to the planet's extreme greenhouse effect, as the long days and nights allow heat to distribute relatively evenly across the surface. Venus rotates in the opposite direction to most planets in the solar system, a phenomenon called retrograde rotation. If it were possible to stand on Venus's surface and watch the sun, it would rise in the west and set in the east. The reason for this backward rotation remains uncertain, though scientists theorize that a massive collision early in the planet's history may have knocked it into this orientation. Regardless of the cause, Venus has maintained this reverse spin for billions of years, a testament to the stability of planetary motion once established. The planet's thick atmosphere creates a pressure at the surface equivalent to being 900 meters underwater on Earth. This crushing pressure remains constant across the entire planet, creating conditions that are extreme yet unchanging. The atmosphere is composed primarily of carbon dioxide, with clouds of sulfuric acid that reflect sunlight brilliantly, making Venus the brightest planet in Earth's sky. These clouds form a complete blanket around the planet, moving much faster than the planet's surface rotates. The atmosphere completes a full rotation every 4 Earth days, a phenomenon called superrotation. The winds at cloud level reach speeds of 360 kilometers per hour, yet this violent motion occurs high above the surface, where the air near the ground barely moves at all. The surface temperature on Venus averages 462 degrees Celsius, hot enough to melt lead, and this temperature varies by only a few degrees between day and night, equator and poles. The greenhouse effect that creates this heat is so efficient that Venus maintains nearly constant temperatures across its entire surface. The landscape of Venus features vast volcanic plains, highland regions, and thousands of volcanoes. Some of these volcanoes may still be active, though volcanic eruptions on Venus occur on geological timescales, separated by millions of years. The surface is relatively young in geological terms, perhaps only 300 to 500 million years old, suggesting that massive volcanic resurfacing events have occurred in the planet's past. Yet even these catastrophic events are spaced so far apart in time that they represent a form of geological calm when viewed across billions of years. Venus has no moons, no rings, and no magnetic field generated by its core. The planet orbits the Sun in an almost perfect circle, with an eccentricity of only 0.007, the most circular orbit of any planet. This near-perfect circle means that Venus receives almost exactly the same amount of sunlight throughout its year, adding another layer of constancy to the planet's character. The planet's slow rotation and thick atmosphere create weather patterns that are remarkably stable, with the same basic circulation pattern persisting indefinitely. Earth's magnetic field extends far into space, creating an invisible shield called the magnetosphere. This protective bubble deflects most of the solar wind, preventing harmful charged particles from reaching the surface. The magnetosphere has maintained this protective function for billions of years, quietly safeguarding the development of life. The field is generated by the motion of molten iron in Earth's outer core, a process that continues without interruption as the planet's internal heat slowly dissipates. The magnetic field reverses polarity at irregular intervals, with the north and south magnetic poles switching places. These reversals occur roughly every 200,000 to 300,000 years on average, though the intervals vary considerably. The last reversal occurred about 780,000 years ago, meaning Earth is currently in a relatively long stable period. During a reversal, which takes several thousand years to complete, the magnetic field weakens but does not disappear entirely. Life on Earth has survived numerous magnetic reversals without catastrophic consequences, demonstrating the resilience of biological systems. Earth's atmosphere is composed of 78% nitrogen, 21% oxygen, and trace amounts of other gases. This mixture has remained relatively stable for hundreds of millions of years, maintained by the balance between geological processes and biological activity. The oxygen in the atmosphere is almost entirely produced by photosynthetic organisms, primarily phytoplankton in the oceans. These microscopic organisms convert carbon dioxide and water into oxygen and organic compounds, a process that continues day and night across the planet's oceans. The oceans themselves cover 71% of Earth's surface, containing 97% of the planet's water. The ocean's circulation patterns, driven by differences in temperature and salinity, move water around the globe in predictable cycles that take hundreds of years to complete. The deepest point in the ocean, the Mariana Trench, reaches 11 kilometers below sea level, yet even at this depth, life exists in the form of specialized organisms adapted to extreme pressure. Earth's rotation creates a day-night cycle that has remained constant throughout human history. The planet completes one rotation every 23 hours, 56 minutes, and 4 seconds, a period called a sidereal day. This rotation is gradually slowing due to tidal friction caused by the Moon's gravitational pull, but the change is imperceptible on human timescales. The Moon itself is slowly moving away from Earth at a rate of about 3.8 centimeters per year, a gentle separation that will continue for billions of years. The Moon's gravitational influence creates tides in Earth's oceans, a rhythmic rise and fall of sea level that occurs twice daily. These tides have repeated billions of times throughout Earth's history, providing a reliable pattern that many organisms have evolved to utilize. The Earth's axial tilt of 23.5 degrees creates the seasons, a cycle that repeats annually as the planet orbits the Sun. This tilt has remained relatively stable over millions of years, maintained by the Moon's gravitational influence. Without the Moon's stabilizing effect, Earth's axial tilt would vary chaotically, creating extreme climate variations. Instead, the seasons follow a predictable pattern that has allowed complex ecosystems to develop and thrive. Mars once had liquid water flowing across its surface. The evidence is written in the landscape, preserved in river valleys, deltas, and lake beds that dried up billions of years ago. These ancient waterways remain visible today, their channels carved into the Martian surface like fossilized memories of a wetter past. The largest of these features, Valles Marineris, stretches 4,000 kilometers across the planet's surface, dwarfing Earth's Grand Canyon. This massive canyon system was formed by a combination of tectonic activity and water erosion, though the exact processes remain subjects of gentle scientific inquiry. Mars rotates at nearly the same rate as Earth, with a day lasting 24 hours and 37 minutes. This similarity means that day-night cycles on Mars feel familiar, a connection across the vast distance between the two planets. The Martian year, however, lasts 687 Earth days, nearly twice as long as Earth's year. Mars experiences seasons like Earth, thanks to an axial tilt of 25 degrees, very close to Earth's 23.5 degrees. However, Mars's elliptical orbit causes more extreme seasonal variations, with southern hemisphere summers being shorter but more intense than those in the northern hemisphere. The planet's thin atmosphere, composed primarily of carbon dioxide, creates surface pressures only 0.6% of Earth's atmospheric pressure. This thin atmosphere cannot retain much heat, causing dramatic temperature swings between day and night. Temperatures can reach 20 degrees Celsius during summer days at the equator, but plummet to -73 degrees Celsius on average across the planet. The polar regions feature permanent ice caps composed of water ice and frozen carbon dioxide. These ice caps grow and shrink with the seasons in a predictable pattern, with the carbon dioxide sublimating into the atmosphere during summer and freezing out again during winter. Beneath the carbon dioxide ice lies water ice, representing a substantial reservoir of frozen water that has remained stable for millions of years. Mars has two small moons, Phobos and Deimos, both irregularly shaped and likely captured asteroids. Phobos orbits so close to Mars that it completes 3 orbits per Martian day, rising in the west and setting in the east from the perspective of someone on the Martian surface. Phobos is gradually spiraling inward and will eventually be torn apart by tidal forces, though this process will take tens of millions of years. The largest volcano in the solar system, Olympus Mons, rises 21 kilometers above the surrounding plains on Mars. This shield volcano is so massive that it would cover the entire state of Arizona, yet its slopes are so gentle that climbing it would feel like walking up a gradual incline. Olympus Mons is no longer active, having last erupted perhaps 25 million years ago, though this is recent in geological terms. The volcano grew to its enormous size because Mars lacks plate tectonics, allowing volcanic hotspots to remain in one location for billions of years, building up layer upon layer of lava. The Martian surface is covered in iron oxide, giving the planet its distinctive reddish color. This rust formed over billions of years as iron minerals reacted with oxygen in the atmosphere and water. The process occurred gradually, transforming the planet's appearance over geological time. Today, dust storms occasionally engulf the entire planet, but these events follow seasonal patterns and eventually subside, returning Mars to its characteristic calm. Jupiter's Great Red Spot is a storm that has been raging for at least 350 years, possibly much longer. This anticyclonic storm is large enough to contain 2 or 3 Earths, yet it has been gradually shrinking over the past century. Observations from the 1800s suggest the spot was once twice its current size, though the rate of shrinkage has varied over time. Despite this slow contraction, the Great Red Spot shows no signs of disappearing entirely and may persist for many more centuries. The storm rotates counterclockwise, completing one full rotation every 6 days. Wind speeds at the edge of the storm reach 430 kilometers per hour, yet this violent motion has maintained a stable pattern for longer than human civilization has existed. The spot's distinctive red color comes from complex organic molecules created by ultraviolet light interacting with Jupiter's atmospheric chemicals. The exact composition remains uncertain, but the color has remained remarkably consistent throughout the period of human observation. Jupiter itself is the largest planet in the solar system, with a mass more than twice that of all other planets combined. The planet is composed primarily of hydrogen and helium, the same elements that make up the Sun, though in different proportions. Jupiter lacks a solid surface, with its atmosphere gradually transitioning to liquid hydrogen at greater depths. The pressure at Jupiter's core reaches 4,500 times Earth's atmospheric pressure, creating conditions where hydrogen behaves like a liquid metal. This metallic hydrogen layer generates Jupiter's powerful magnetic field, which extends millions of kilometers into space. The magnetosphere is so large that if it were visible from Earth, it would appear several times larger than the full moon in the sky. Jupiter's rapid rotation, completing one full turn every 9 hours and 55 minutes, creates powerful winds and distinctive cloud bands that circle the planet. These bands represent different atmospheric layers moving at different speeds, creating stable patterns that have persisted for as long as humans have observed Jupiter. The planet's fast rotation also causes significant equatorial bulge, making Jupiter noticeably flattened at the poles. The difference between the equatorial and polar diameters is about 9,000 kilometers, visible even through small telescopes. Jupiter emits more heat than it receives from the Sun, radiating infrared energy generated by the slow gravitational contraction of the planet. This internal heat source has powered Jupiter's atmospheric dynamics for billions of years and will continue for billions more. The planet's atmosphere features complex weather patterns, including lightning strikes thousands of times more powerful than those on Earth. These lightning bolts occur deep within Jupiter's clouds, occasionally visible as bright flashes when viewed from the right angle. The planet also experiences auroras at its poles, created when charged particles from the solar wind interact with Jupiter's magnetic field. These auroras are hundreds of times brighter than Earth's auroras and remain permanently active, glowing constantly in ultraviolet wavelengths. Jupiter's gravitational influence has shaped the entire solar system. The planet's massive gravity deflects many comets and asteroids, either capturing them or flinging them out of the solar system entirely. This gravitational housekeeping has likely protected the inner planets from countless impacts over the solar system's history. Jupiter has 95 known moons, but 4 of them stand out as particularly significant. Io, Europa, Ganymede, and Callisto were discovered by Galileo Galilei in 1610, making them among the first objects found orbiting another planet. These 4 moons are large enough to be visible with binoculars, and their regular motion around Jupiter can be observed changing from night to night. The moons are locked in a gravitational resonance, with Io completing 4 orbits for every 2 orbits of Europa and every 1 orbit of Ganymede. This mathematical relationship, called a Laplace resonance, has remained stable for billions of years. Io is the most volcanically active body in the solar system, with hundreds of volcanoes dotting its surface. The moon's volcanic activity is powered by tidal heating, as Jupiter's gravity constantly flexes Io's interior, generating tremendous amounts of heat. Sulfur compounds erupted by these volcanoes give Io its distinctive yellow, orange, and red coloration. Some volcanic plumes on Io reach heights of 300 kilometers above the surface, ejecting material into space. Despite this violent geological activity, Io's volcanism follows predictable patterns, with certain volcanoes erupting regularly on schedules that can be anticipated. The Moon completes 1 orbit around Jupiter every 42.5 hours, always keeping the same face toward the giant planet. Europa, the second Galilean moon, has a surface of water ice that may cover a global ocean of liquid water. The ice shell is relatively thin, perhaps only 15 to 25 kilometers thick, floating atop an ocean that could be 60 to 150 kilometers deep. This ocean contains more water than all of Earth's oceans combined, maintained in liquid form by tidal heating similar to that which powers Io's volcanoes. Europa's surface is remarkably smooth, with few impact craters, suggesting that geological processes regularly resurface the Moon. The ice is crisscrossed with dark linear features called lineae, which may be cracks in the ice where warmer water has welled up from below. The ocean beneath Europa's ice remains one of the most intriguing potential habitats for life beyond Earth, though any organisms living there would exist in complete darkness, far from sunlight. Ganymede is the largest moon in the solar system, even larger than the planet Mercury. The moon has its own magnetic field, the only moon known to possess one, generated by convection in a liquid iron core. Ganymede's surface shows 2 distinct types of terrain: dark, heavily cratered regions and lighter, grooved terrain with fewer craters. The grooved terrain formed more recently, perhaps created by tectonic activity driven by tidal heating. Like Europa, Ganymede may harbor a subsurface ocean, though it would lie beneath a much thicker ice shell. Callisto, the outermost Galilean moon, is the most heavily cratered object in the solar system. The moon's ancient surface has accumulated impact craters for billions of years, creating a record of the solar system's violent early history. Unlike the other Galilean moons, Callisto shows little evidence of internal geological activity. The moon's surface has remained largely unchanged for billions of years, a frozen testament to the early solar system. Callisto may also have a subsurface ocean, though evidence for this remains less certain than for Europa or Ganymede. The 4 Galilean moons orbit Jupiter in a plane aligned with the planet's equator, creating a miniature solar system that mirrors the organization of planets around the Sun. Saturn's rings are the most extensive and visible ring system in the solar system. The rings extend from 7,000 kilometers to 80,000 kilometers above Saturn's equator, yet they are remarkably thin, with a typical thickness of only 10 meters. This extreme thinness makes the rings proportionally thinner than a sheet of paper. The rings are composed primarily of water ice particles, ranging in size from tiny grains to house-sized boulders. Each particle orbits Saturn independently, following Kepler's laws of planetary motion. The rings are divided into several main sections, designated by letters in the order of their discovery. The most prominent rings, visible from Earth with a small telescope, are the A ring and B ring, separated by a gap called the Cassini division. This gap, 4,800 kilometers wide, is not actually empty, but contains less dense ring material. The gap is maintained by gravitational resonances with Saturn's moon Mimas, whose orbit creates regions where ring particles cannot remain stable. The rings display intricate structure, with thousands of individual ringlets visible in detailed images. Some of these structures are created by small moons orbiting within or near the rings, called shepherd moons. These moons gravitationally sculpt the ring material, creating sharp edges and clearing gaps. The rings are not solid structures, but rather countless individual particles, each reflecting sunlight and creating the brilliant appearance visible from Earth. The origin of Saturn's rings remains uncertain. They may be the remnants of a moon that was destroyed by a collision or torn apart by tidal forces, or they may be leftover material from Saturn's formation that never coalesced into a moon. Recent research suggests the rings may be relatively young, perhaps only 100 to 200 million years old, though this conclusion remains debated. Regardless of their age, the rings follow stable, predictable orbits that will persist for millions of years into the future. Saturn's rings cast shadows on the planet's cloud tops, creating dark bands that move across the planet as Saturn orbits the Sun. Twice during Saturn's 29.5-year orbit, the rings appear edge-on from Earth's perspective, becoming nearly invisible due to their extreme thinness. These ring plane crossings occur approximately every 15 years, providing opportunities to observe Saturn's moons without the glare of the rings. The rings also create a phenomenon called ring rain, where charged particles from the rings spiral down into Saturn's atmosphere. This process gradually erodes the rings, though at a rate slow enough that the rings will persist for tens of millions of years. Saturn rotates rapidly, completing one full rotation every 10 hours and 33 minutes. This fast rotation creates strong winds and distinctive cloud bands similar to Jupiter's, though less colorful. The planet's rapid rotation also causes significant equatorial bulge, making Saturn the most flattened planet in the solar system. The difference between the equatorial and polar diameters is about 10%, clearly visible in photographs. Saturn's low density, less than that of water, means the planet would float if placed in a sufficiently large ocean. This low density results from Saturn's composition, primarily hydrogen and helium, with only a small rocky core. Titan is Saturn's largest moon and the second largest moon in the solar system. The Moon possesses a thick atmosphere, the only moon with a substantial atmosphere, composed primarily of nitrogen with traces of methane and other organic compounds. The atmospheric pressure at Titan's surface is 1.5 times that of Earth's atmosphere, making it the only place beyond Earth where a human could walk without a pressure suit, though a spacesuit would still be necessary due to the cold and lack of oxygen. Titan's atmosphere is so thick and hazy that the surface was not visible until the Cassini spacecraft dropped the Huygens probe through the clouds in 2005. The probe revealed a landscape of rounded hills, river channels, and smooth plains. The surface temperature on Titan averages -179 degrees Celsius, cold enough that water ice is as hard as rock. At these temperatures, methane and ethane exist as liquids, creating weather cycles similar to Earth's water cycle. Clouds of methane form in Titan's atmosphere, producing rain that falls to the surface and collects in lakes and seas. The largest of these liquid bodies, Kraken Mare, covers an area larger than the Caspian Sea on Earth. These lakes are filled with liquid methane and ethane, creating the only stable bodies of surface liquid known to exist beyond Earth. The lakes show shorelines, islands, and depth variations, features that mirror terrestrial bodies of water. Titan's methane cycle includes evaporation, cloud formation, precipitation, surface runoff, and infiltration into the ground, creating a complete hydrological system. River channels carved by liquid methane wind across Titan's surface, some of them hundreds of kilometers long. These rivers flow sluggishly due to Titan's low gravity and the viscosity of liquid methane, but they transport sediment and shape the landscape just as rivers do on Earth. The surface of Titan is relatively young, with few impact craters visible, suggesting that geological processes regularly resurface the Moon. Wind-blown dunes cover large regions near Titan's equator, created by particles of organic compounds blown by Titan's gentle winds. These dunes are hundreds of meters tall and stretch for hundreds of kilometers, creating patterns visible from orbit. The organic compounds that form these dunes are created in Titan's atmosphere when sunlight breaks apart methane molecules, allowing the fragments to recombine into more complex molecules. This atmospheric chemistry produces a constant rain of organic particles that settles onto Titan's surface, gradually accumulating over millions of years. Titan may have a subsurface ocean of liquid water beneath its icy crust, maintained by tidal heating from Saturn's gravity. This ocean, if it exists, would be separated from the surface by tens of kilometers of ice, making it inaccessible to direct observation. Titan orbits Saturn every 16 days, always keeping the same face toward the planet due to tidal locking. The Moon's orbit is nearly circular, maintaining a consistent distance from Saturn. From Titan's surface, Saturn would appear enormous in the sky, though the view would be obscured by Titan's thick haze. The Moon's slow rotation, synchronized with its orbital period, creates day-night cycles that last about 16 Earth days. Despite the long days, temperature variations between day and night are minimal due to the thick atmosphere, which distributes heat efficiently. Uranus rotates on its side with an axial tilt of 98 degrees. This extreme tilt means that Uranus's poles alternately point almost directly at the Sun during the planet's 84-year orbit. Each pole experiences 42 years of continuous sunlight followed by 42 years of darkness. This unusual orientation likely resulted from a massive collision early in the solar system's history, when a large object struck Uranus with enough force to knock it onto its side. Despite this violent origin, Uranus has maintained its tilted orientation for billions of years, demonstrating the stability of planetary rotation once established. The planet's rotation period is 17 hours and 14 minutes. though measuring this precisely is difficult because Uranus lacks a solid surface and different parts of its atmosphere rotate at different speeds. Uranus is an ice giant composed primarily of water, methane, and ammonia ices surrounding a rocky core. The planet's distinctive blue-green color comes from methane in the upper atmosphere, which absorbs red light and reflects blue and green wavelengths. The atmosphere appears remarkably uniform, with few visible cloud features, giving Uranus a serene, featureless appearance. This calmness is somewhat deceptive, as wind speeds on Uranus can reach 900 kilometers per hour, though these winds blow in the same direction as the planet's rotation, creating less visible turbulence than on Jupiter or Saturn. Uranus has a system of 13 narrow rings, discovered in 1977 when the planet passed in front of a star and the rings blocked the starlight. These rings are much darker than Saturn's rings, composed of material that reflects very little light. The rings are narrow and well-defined, maintained by shepherd moons that gravitationally confine the ring particles. The innermost rings are only a few kilometers wide, while the outermost ring is broader and more diffuse. Uranus has 27 known moons, all named after characters from the works of William Shakespeare and Alexander Pope. The 5 largest moons are Miranda, Ariel, Umbriel, Titania, and Oberon. These moons orbit in the plane of Uranus's equator, meaning their orbits are nearly perpendicular to the planet's orbital plane around the Sun. This unusual configuration results from Uranus's extreme axial tilt. The moons are composed primarily of ice and rock, with surfaces showing various degrees of geological activity. Miranda, the smallest of the 5 major moons, has one of the most geologically diverse surfaces in the solar system, with regions of different ages and terrains jumbled together. The moon features a massive cliff called Verona Rupes, which rises 20 kilometers high, making it the tallest known cliff in the solar system. Despite this dramatic topography, Miranda's geological activity ceased long ago, leaving these features frozen in time. Uranus generates very little internal heat compared to the other giant planets, while Jupiter, Saturn, and Neptune all emit more heat than they receive from the Sun. Uranus emits almost no excess heat. This lack of internal heat contributes to the planet's relatively calm atmosphere and uniform appearance. The reason for this heat deficiency remains uncertain, though it may be related to the collision that tilted the planet, perhaps allowing much of the planet's internal heat to escape into space. Uranus's magnetic field is unusual, tilted 59 degrees from the planet's rotational axis and offset from the planet's center. This creates a complex, asymmetric magnetosphere unlike any other in the solar system. As Uranus rotates, the magnetic field wobbles, creating constantly changing conditions in the space around the planet. Neptune is the most distant planet in the solar system, orbiting at an average distance of 4.5 billion kilometers from the Sun. At this distance, sunlight is 900 times dimmer than on Earth, yet Neptune receives enough solar energy to drive the fastest winds in the solar system. Wind speeds on Neptune reach up to 2,100 kilometers per hour, faster than the speed of sound in Earth's atmosphere. These supersonic winds blow primarily westward, opposite to the planet's rotation, creating weather patterns that remain poorly understood. Neptune's atmosphere displays more visible features than Uranus, including dark spots that are massive storm systems. The most famous of these was the Great Dark Spot, observed by Voyager 2 in 1989. This storm was roughly the size of Earth and rotated counterclockwise, similar to Jupiter's Great Red Spot. However, when the Hubble Space Telescope observed Neptune in 1994, the Great Dark Spot had disappeared, demonstrating that Neptune's storms are more transient than Jupiter's. New dark spots have appeared and disappeared since then, showing that Neptune's atmosphere is dynamic and constantly changing, yet these changes follow patterns that repeat over time. Neptune appears deep blue due to methane in its atmosphere, which absorbs red light. The planet's blue color is more vivid than Uranus's, suggesting that an unknown component contributes to the coloration. Neptune emits 2.6 times more heat than it receives from the Sun, indicating a strong internal heat source. This internal heat drives the planet's atmospheric circulation and contributes to the powerful winds. The heat comes from the gradual gravitational contraction of the planet, a process that will continue for billions of years as Neptune slowly cools. Neptune completes one orbit around the Sun every 165 Earth years, meaning the planet has completed only one full orbit since its discovery in 1846. The planet's discovery was itself a triumph of mathematical prediction, as astronomers calculated Neptune's position based on irregularities in Uranus's orbit before the planet was actually observed. Neptune rotates once every 16 hours and 6 minutes, creating day-night cycles that are irrelevant at such distance from the Sun, where even daytime is dim twilight. Neptune has 14 known moons, the largest of which is Triton. This moon is unusual in several ways, most notably its retrograde orbit, meaning it orbits Neptune in the opposite direction to the planet's rotation. This backward orbit indicates that Triton was captured by Neptune's gravity rather than forming alongside the planet. Triton is gradually spiraling inward and will eventually be torn apart by tidal forces, though this process will take billions of years. The moon's surface is extremely cold, with temperatures around -235 degrees Celsius, making it one of the coldest surfaces in the solar system. Despite these frigid conditions, Triton is geologically active, with nitrogen geysers erupting from its surface. These geysers shoot nitrogen gas and dark particles up to 8 kilometers high, creating dark streaks on Triton's icy surface. The geysers are powered by seasonal heating from the Sun, which is sufficient to vaporize nitrogen ice even at Triton's distance. Neptune has a system of 5 faint rings, discovered during ground-based observations and confirmed by Voyager 2. These rings are composed of dark material and are much less prominent than Saturn's rings. Some of the rings contain bright clumps of material called arcs, which remain confined to specific regions rather than spreading evenly around the planet. The asteroid belt occupies the region between Mars and Jupiter, extending from approximately 2.2 to 3.2 astronomical units from the Sun. This belt contains millions of rocky bodies, ranging from tiny pebbles to Ceres, a dwarf planet with a diameter of 940 kilometers. Despite the large number of asteroids, the belt is mostly empty space. The total mass of all asteroids combined is less than that of Earth's moon, and the average distance between asteroids is measured in millions of kilometers. Spacecraft routinely pass through the asteroid belt without any need for evasive maneuvers, as the probability of collision is extremely low. The asteroids orbit the Sun following the same physical laws that govern planetary motion, each following an elliptical path determined by its velocity and distance from the Sun. The asteroid belt contains several distinct families of asteroids, groups that share similar orbits and compositions, likely fragments from larger parent bodies broken apart by ancient collisions. These families demonstrate that the asteroid belt's current configuration is the result of billions of years of collisional evolution, with larger bodies gradually breaking down into smaller pieces. The largest asteroid, Ceres, contains approximately 1/3 of the belt's total mass. Ceres is large enough for its own gravity to have pulled it into a spherical shape, qualifying it as a dwarf planet. The dwarf planet has a differentiated interior with a rocky core and possibly a subsurface ocean of liquid water beneath an icy mantle. Ceres's surface features bright spots that are deposits of salts left behind when subsurface briny water reached the surface and evaporated. These bright regions suggest that Ceres has been geologically active in the relatively recent past, with some activity possibly continuing today. The asteroid belt structure is influenced by gravitational resonances with Jupiter. Regions where asteroids would orbit the Sun in periods that are simple fractions of Jupiter's orbital period are largely empty, creating gaps called Kirkwood gaps. These gaps occur at orbital periods of 1/2, 1/3, 2/5, and 3/7 of Jupiter's period. Asteroids that wander into these resonance regions experience repeated gravitational tugs from Jupiter that eventually push them into different orbits. This gravitational housekeeping has been ongoing for billions of years, creating the belt's current structure. Most asteroids rotate relatively slowly, taking several hours to complete one rotation. Some asteroids are elongated or irregularly shaped, tumbling as they orbit the Sun. A few asteroids have small moons orbiting them, miniature systems held together by weak mutual gravity. The asteroid Ida, for example, has a small moon called Dactyl, only 1.4 kilometers across. These binary asteroids likely formed when collisions broke pieces off larger bodies, with the fragments remaining gravitationally bound. The asteroid belt represents material that never coalesced into a planet, prevented from accumulating by Jupiter's gravitational influence. The region where the belt exists would likely have formed a planet if Jupiter had not disrupted the process early in the solar system's history. Instead, the asteroids remain as scattered remnants, a frozen record of the solar system's formation. The belt's asteroids are composed of various materials, with compositions varying by distance from the Sun. Inner belt asteroids tend to be rocky, while outer belt asteroids contain more water ice and organic compounds. Comets are icy bodies that orbit the Sun on highly elliptical paths, spending most of their time in the cold outer reaches of the solar system. When a comet's orbit brings it close to the Sun, solar heat vaporizes ice from the comet's surface, creating a glowing coma and often spectacular tails that can stretch millions of kilometers. These tails always point away from the Sun, pushed by solar radiation and the solar wind. Comets have two distinct tails: a dust tail composed of small solid particles and an ion tail composed of ionized gas. The dust tail curves slightly due to the particle's orbital motion, while the ion tail points straight away from the Sun. Despite their dramatic appearance, comets are relatively small, with nuclei typically only a few kilometers across. Halley's Comet, perhaps the most famous comet, has a nucleus approximately 15 kilometers long and 8 kilometers wide, shaped like a peanut. This comet orbits the Sun every 76 years, a period that has remained remarkably consistent throughout recorded history. Historical records of Halley's Comet sightings extend back to 240 BCE, documenting the comet's regular returns across more than 2 millennia. The comet's orbit takes it from 0.6 astronomical units from the Sun at closest approach to 35 astronomical units at its farthest point, well beyond Neptune's orbit. Each time Halley's Comet passes close to the Sun, it loses approximately 250 million tons of material through sublimation, gradually shrinking over time. At this rate, the comet will survive for approximately 2,300 more orbits, or about 175,000 years, before it completely disintegrates. Comets originate from two main regions of the solar system. Short-period comets, with orbital periods less than 200 years, come from the Kuiper belt, a region beyond Neptune's orbit containing millions of icy bodies. Long-period comets, with orbital periods of thousands or millions of years, originate from the Oort cloud, a spherical shell of comets surrounding the solar system at distances up to 100,000 astronomical units. The Oort cloud contains trillions of comets, most of which will never approach the Sun closely enough to become visible from Earth. Occasionally, gravitational perturbations from passing stars or giant molecular clouds nudge Oort cloud comets into orbits that bring them into the inner solar system. These long-period comets may take millions of years to complete a single orbit. When comets repeatedly pass close to the Sun, they gradually lose their volatile materials and may eventually become inactive, resembling asteroids more than comets. Some asteroids in the asteroid belt may be extinct comet nuclei that have lost all their ice. The transition from active comet to dormant asteroid occurs gradually over many orbits as the comet's surface becomes covered with a layer of dust that insulates the remaining ice beneath. Cometary debris spreads along the comet's orbital path, creating streams of particles that Earth encounters annually. When Earth passes through these debris streams, the particles enter the atmosphere and burn up, creating meteor showers. Each meteor shower is associated with a specific comet, and the showers occur at the same time each year as Earth returns to the same point in its orbit. The Perseid meteor shower, for example, is caused by debris from comet Swift-Tuttle, while the Orionid shower comes from Halley's Comet. These annual meteor showers provide a reliable celestial display, a gentle reminder of the comets that created them. Beyond Neptune's orbit lies a region populated by thousands of icy bodies, collectively called trans-Neptunian objects. This region includes several dwarf planets, bodies large enough for gravity to pull them into spherical shapes, but not large enough to clear their orbital neighborhoods of other debris. The most famous of these is Pluto, discovered in 1930 and reclassified as a dwarf planet in 2006. Pluto orbits the Sun every 248 years at an average distance of 39.5 astronomical units, though its elliptical orbit brings it as close as 29.7 astronomical units and as far as 49.3 astronomical units. The dwarf planet is smaller than Earth's moon, with a diameter of 2,377 kilometers. Pluto has 5 known moons, the largest of which is Charon, about half Pluto's diameter. Charon is so large relative to Pluto that the two bodies orbit a common center of mass located between them, creating a binary system rather than a simple planet-moon system. Pluto and Charon are tidally locked to each other, always showing the same faces toward each other as they orbit their common center every 6.4 days. The New Horizons spacecraft flew past Pluto in 2015, revealing a world of surprising geological complexity. Pluto's surface features vast plains of nitrogen ice, mountains of water ice rising several kilometers high, and possible cryovolcanoes that erupt water and ammonia instead of molten rock. The plains, named Sputnik Planitia, show evidence of convection cells where warmer nitrogen ice rises and cooler ice sinks, creating a slow churning motion that resurfaces the plains every few 100,000 years. This geological activity was unexpected for such a small, distant world, demonstrating that internal heat sources can drive geological processes even in the outer solar system. Pluto has a thin atmosphere composed primarily of nitrogen with traces of methane and carbon monoxide. This atmosphere freezes and falls to the surface as snow when Pluto is farthest from the Sun, then sublimates back into gas as the dwarf planet approaches the Sun. The atmospheric pressure varies by a factor of 100 over Pluto's orbital period, creating seasonal changes that last decades. Eris, another dwarf planet, is slightly smaller than Pluto but more massive, with a highly reflective surface of methane ice. Eris orbits at an average distance of 68 astronomical units, taking 558 years to complete one orbit. The dwarf planet's orbit is highly inclined and elliptical, taking it as far as 97.5 astronomical units from the Sun. Eris has one known moon, Dysnomia, which orbits every 16 days. The discovery of Eris in 2005 prompted the debate that led to Pluto's reclassification, as astronomers realized that many similar objects likely existed in the outer solar system. Makemake and Haumea are additional dwarf planets in the trans-Neptunian region. Makemake is slightly smaller than Pluto and takes 306 years to orbit the Sun. Haumea is notable for its rapid rotation, completing one turn every 4 hours, which has stretched it into an elongated ellipsoid shape. Haumea has 2 small moons and a ring system, making it the first known trans-Neptunian object with rings. These distant dwarf planets represent a population of objects that formed in the outer solar system and have remained largely unchanged since the solar system's formation. They preserve information about the conditions and materials present in the early solar system, serving as frozen time capsules from 4.6 billion years ago. The Sun continuously emits a stream of charged particles called the solar wind, which flows outward through the solar system at speeds of 400 to 800 kilometers per second. This wind is composed primarily of electrons and protons, with smaller amounts of heavier ions. The solar wind originates in the Sun's corona, the outermost layer of the solar atmosphere, where temperatures reach millions of degrees. At these extreme temperatures, particles move fast enough to escape the Sun's gravity, streaming outward into space. The solar wind is not uniform, but varies in speed and density, depending on conditions in the corona. Fast solar wind streams originate from coronal holes, regions where the Sun's magnetic field lines extend into space rather than looping back to the surface. These fast streams can reach speeds of 800 kilometers per second. Slower solar wind comes from the edges of coronal streamers, regions where the magnetic field is more complex. The solar wind carries the Sun's magnetic field with it, creating the interplanetary magnetic field that pervades the solar system. This magnetic field has a spiral structure shaped by the Sun's rotation. As the Sun rotates once every 27 days, the magnetic field lines carried by the solar wind curve into spirals, similar to water streams from a rotating sprinkler. The solar wind interacts with planetary magnetic fields, creating magnetospheres around planets that have substantial magnetic fields. For planets without magnetic fields, like Mars and Venus, the solar wind interacts directly with the upper atmosphere, gradually stripping away atmospheric particles over billions of years. Earth's magnetosphere deflects most of the solar wind, but some particles enter near the poles, where they collide with atmospheric gases and create auroras. The solar wind extends far beyond the orbits of the planets, creating a bubble called the heliosphere that encompasses the entire solar system. The boundary where the solar wind slows down and becomes subsonic is called the termination shock, located approximately 90 astronomical units from the Sun. Beyond this boundary lies the heliosheath, a region where the solar wind continues outward but at slower speeds. The outermost boundary of the heliosphere, called the heliopause, is where the solar wind finally stops and interstellar space begins. The Voyager 1 spacecraft crossed the heliopause in 2012 at a distance of 121 astronomical units from the Sun, becoming the first human-made object to enter interstellar space. Voyager 2 followed in 2018, crossing at 119 astronomical units. The exact shape and size of the heliosphere vary with the solar cycle, expanding during solar minimum and contracting during solar maximum. The solar wind's pressure also varies with solar activity, creating a heliosphere that breathes, slowly expanding and contracting over the 11-year solar cycle. The solar wind protects the inner solar system from galactic cosmic rays, high-energy particles that originate outside the solar system. The heliosphere acts as a shield, deflecting many of these cosmic rays and reducing the radiation exposure experienced by the planets. Without this protection, the radiation environment in the inner solar system would be significantly harsher, potentially affecting the development and persistence of life on Earth. The solar wind will continue flowing as long as the sun exists, maintaining the heliosphere for billions of years into the future. Several planets in the solar system generate magnetic fields through a process called the dynamo effect. This process requires a conducting fluid, such as molten iron, moving within the planet's interior. The motion of this conducting material generates electric currents, which in turn create magnetic fields. Earth's magnetic field is generated by convection in the outer core, where liquid iron circulates due to heat escaping from the inner core. This process has continued for billions of years, maintaining Earth's protective magnetosphere. The magnetic field extends far into space, creating a region called the magnetosphere that shields Earth from the solar wind. The magnetosphere is compressed on the side facing the sun and stretched into a long tail on the night side, creating an asymmetric structure that extends hundreds of thousands of kilometers into space. Mercury also has a magnetic field, though it is much weaker than Earth's, only about 1% as strong. This weak field is generated by a partially molten core, which remains liquid despite Mercury's small size due to the presence of sulfur, which lowers the melting point of iron. Mercury's magnetosphere is tiny compared to Earth's, extending only about 1,000 kilometers above the planet's surface. Despite its small size, this magnetosphere provides some protection from the solar wind, though much less than Earth's field provides. Jupiter has the strongest magnetic field of any planet, approximately 20,000 times stronger than Earth's field. This powerful field is generated by convection in Jupiter's metallic hydrogen layer, where hydrogen under extreme pressure behaves like a liquid metal. Jupiter's magnetosphere is enormous, extending up to 7 million kilometers in the direction of the Sun and stretching even farther in the opposite direction. If the magnetosphere were visible from Earth, it would appear larger than the full moon in the sky. The magnetosphere traps charged particles, creating intense radiation belts far more dangerous than Earth's Van Allen belts. These radiation belts pose significant challenges for spacecraft visiting Jupiter, requiring extensive shielding to protect sensitive electronics. Saturn also has a strong magnetic field, though weaker than Jupiter's, generated by convection in a metallic hydrogen layer similar to Jupiter's. Saturn's magnetosphere is large but more symmetric than Jupiter's, extending about 1.5 million kilometers in the direction of the Sun. The magnetosphere interacts with Saturn's rings and moons, creating complex plasma interactions. Enceladus, one of Saturn's moons, ejects water vapor from geysers at its south pole, and this water becomes ionized in Saturn's magnetosphere, creating a torus of plasma around Saturn at Enceladus's orbital distance. Uranus and Neptune have unusual magnetic fields that are tilted significantly from their rotational axes and offset from the planet's centers. Uranus's magnetic field is tilted 59 degrees from its rotational axis, while Neptune's is tilted 47 degrees. These unusual configurations create complex, asymmetric magnetospheres, unlike those of any other planets. The magnetic fields of Uranus and Neptune are likely generated by convection in layers of water, ammonia, and methane compounds in the planet's interiors, rather than in metallic hydrogen layers. Venus and Mars lack significant magnetic fields generated by their cores. Venus likely lacks a dynamo because its core does not have the necessary convection, possibly because the planet's slow rotation does not provide enough Coriolis effect to organize the flow patterns needed for dynamo action. Mars may have had a magnetic field in its distant past, but the planet's core has cooled to the point where it no longer generates a field. 4 planets in the solar system have ring systems: Jupiter, Saturn, Uranus, and Neptune. These rings formed through different processes but share common characteristics. All ring systems exist within a region called the Roche limit, the distance from a planet within which tidal forces prevent material from coalescing into a moon. Inside this limit, any moon-sized object would be torn apart by the planet's gravity, and loose material cannot accrete into larger bodies. Ring systems represent material that either never formed into moons or came from moons that were destroyed. Saturn's rings are by far the most extensive and visible, composed primarily of water ice particles that range from microscopic grains to house-sized boulders. The rings reflect sunlight brilliantly, making them easily visible from Earth with a small telescope. The rings are organized into several main divisions, with the brightest being the A and B rings. The Cassini division, a 4,800-kilometer gap between these rings, is maintained by gravitational resonances with Saturn's moon Mimas. The rings show intricate structure at all scales, with thousands of individual ringlets visible in detailed images. Some of these structures are created by small moons embedded within or near the rings, called shepherd moons. These moons gravitationally confine ring material, creating sharp edges and clearing gaps. The rings are remarkably thin, typically only 10 meters thick, though they extend tens of thousands of kilometers radially. This extreme thinness results from collisions between ring particles, which gradually flatten the system into a thin disk. Jupiter's rings are much fainter than Saturn's, composed of dark dust particles rather than bright ice. The main ring is only about 30 kilometers thick and extends from 122,500 to 129,000 kilometers from Jupiter's center. The ring is continuously replenished by dust knocked off small moons by micrometeorite impacts. Without this continuous supply, the ring would disappear within a few thousand years as particles spiral into Jupiter or are lost to space. Jupiter also has a faint gossamer ring extending outward from the main ring and a halo ring extending inward toward the planet. These components create a complete but faint ring system that was unknown until the Voyager spacecraft imaged it in 1979. Uranus has 13 known rings, all narrow and dark, composed of material that reflects very little light. The rings were discovered in 1977 when Uranus passed in front of a star and the rings blocked the starlight before and after the planet itself did. The rings are remarkably narrow, with the widest being only about 100 kilometers across and most being less than 10 kilometers wide. The particles in Uranus's rings are dark, possibly covered with organic compounds that have been darkened by radiation. The rings are confined by shepherd moons that keep the particles from spreading out. Neptune's rings are similar to Uranus's, narrow and dark, but with an unusual feature. Some of the rings contain bright arcs, regions where material is concentrated rather than spread evenly around the planet. These arcs are confined by gravitational resonances with Neptune's moon Galatea, which prevents the material from spreading uniformly. The arcs are named Liberté, Égalité, Fraternité, and Courage, and they have remained stable since their discovery in 1989. All planetary ring systems are dynamic, with particles constantly colliding, fragmenting, and being lost from the system. Ring systems require continuous replenishment to remain visible over long timescales. Several moons in the outer solar system display active geysers that erupt water or other volatiles into space. These geysers demonstrate that geological activity continues even on small, distant worlds, powered by tidal heating or residual internal heat. The most famous geysers are found on Enceladus, a small moon of Saturn only 504 kilometers in diameter. The Cassini spacecraft discovered jets of water vapor and ice particles erupting from fractures near Enceladus's south pole, reaching heights of several hundred kilometers above the surface. These geysers erupt continuously, releasing approximately 200 kilograms of material per second. The water comes from a subsurface ocean that lies beneath an ice shell perhaps 20 to 30 kilometers thick. The ocean is kept liquid by tidal heating as Saturn's gravity flexes Enceladus's interior, generating friction and heat. The geysers erupt through a series of parallel fractures called tiger stripes, which are warmer than the surrounding terrain. The temperature in these fractures reaches as high as -70 degrees Celsius, remarkably warm compared to the average surface temperature of -198 degrees Celsius. The geyser material contains water vapor, ice particles, salts, and organic molecules, providing strong evidence that Enceladus's ocean is in contact with rock, where chemical reactions could potentially support life. The geysers create a faint ring around Saturn called the E ring, composed of ice particles that have escaped Enceladus's gravity. This ring is the most extensive of Saturn's rings, stretching from the orbit of Mimas to beyond the orbit of Titan, though it is extremely tenuous. Europa, Jupiter's moon, may also have geysers, though the evidence is less certain than for Enceladus. The Hubble Space Telescope has observed what appear to be plumes of water vapor erupting from Europa's surface, reaching heights of 200 kilometers. These plumes, if confirmed, would provide direct access to Europa's subsurface ocean without the need to drill through kilometers of ice. The plumes appear to be intermittent, erupting only at certain times, possibly related to tidal stresses that vary as Europa orbits Jupiter. Triton, Neptune's largest moon, has nitrogen geysers that erupt from its surface. These geysers are driven by solar heating of subsurface nitrogen ice, which vaporizes and builds up pressure until it breaks through the surface. The geysers on Triton are seasonal, occurring during the moon's summer when sunlight, though extremely faint at Neptune's distance, is sufficient to heat the surface. The nitrogen geysers carry dark particles from beneath the surface, which are deposited downwind, creating dark streaks on Triton's icy surface. These streaks can be tens of kilometers long, providing visible evidence of the geyser activity. The geysers demonstrate that even at temperatures of -235 degrees Celsius, geological processes can remain active. The geysers on these moons operate on different principles, but share the common feature of releasing subsurface material into space. This process provides a natural sampling mechanism, allowing spacecraft to study subsurface materials without landing. Future missions may fly through these geyser plumes, collecting samples for analysis and searching for signs of life. The continuous eruption of geysers on Enceladus and the seasonal activity on Triton demonstrate that these processes are stable and long-lasting, likely having continued for millions of years. The geysers represent a gentle form of geological activity, far less violent than volcanic eruptions, but equally significant in shaping these moons' surfaces and providing clues about their internal structure. Orbital resonances occur when two or more orbiting bodies exert regular, periodic gravitational influences on each other due to their orbital periods being related by a ratio of small integers. These resonances can stabilize orbits or destabilize them, depending on the specific configuration. The solar system contains numerous examples of orbital resonances that have persisted for billions of years. The most famous example is the resonance between Jupiter's moons Io, Europa, and Ganymede. For every 4 orbits that Io completes, Europa completes exactly 2 orbits, and Ganymede completes exactly 1 orbit. This 4 to 2 to 1 ratio, called a Laplace resonance, has remained stable throughout the solar system's history. The resonance causes the moon's orbits to remain slightly elliptical rather than circular, which generates tidal heating as Jupiter's gravity flexes the moon's interiors. This tidal heating powers Io's volcanism and may maintain subsurface oceans on Europa and Ganymede. The resonance is self-maintaining, as the gravitational interactions between the moons prevent any of them from drifting out of the resonant configuration. Pluto and Neptune are locked in a 3 to 2 orbital resonance, with Pluto completing 2 orbits for every 3 orbits of Neptune. This resonance prevents the two bodies from ever colliding, even though Pluto's elliptical orbit sometimes brings it closer to the Sun than Neptune. The resonance ensures that whenever Pluto crosses Neptune's orbital distance, Neptune is always far away on the other side of the Sun. This configuration has remained stable for millions of years and will continue for millions more. Many other trans-Neptunian objects share similar resonances with Neptune, creating populations of objects called resonant Kuiper belt objects. The asteroid belt contains gaps called Kirkwood gaps, located at orbital distances where asteroids would be in resonance with Jupiter. These gaps occur at the 3 to 1, 5 to 2, 7 to 3, and 2 to 1 resonances, where an asteroid would orbit the Sun 3, 2.5, 2 1/3, or 2 times for every 1 orbit of Jupiter. Asteroids in these resonant orbits experience repeated gravitational tugs from Jupiter that eventually push them into different orbits, creating the observed gaps. The process takes millions of years, but the cumulative effect is clear in the asteroid belt's structure. Some resonances are stabilizing rather than destabilizing. The Hilda asteroids occupy the 3 to 2 resonance with Jupiter, and this resonance actually protects them from close approaches to Jupiter, keeping them in stable orbits for billions of years. The Trojan asteroids orbit in Jupiter's orbit, 60 degrees ahead of and behind the planet, held in place by a different type of resonance involving Lagrange points. These are special locations where the gravitational forces of Jupiter and the Sun combine to create stable equilibrium points. Thousands of asteroids occupy Jupiter's Trojan points, and similar populations exist at the Trojan points of other planets. Saturn's rings display numerous resonances with the planet's moons. The Cassini division, the prominent gap in Saturn's rings, is maintained by a 2 to 1 resonance with the moon Mimas. Particles in this gap would orbit Saturn twice for every 1 orbit of Mimas, and the repeated gravitational interactions gradually remove particles from this region. Many smaller gaps and ringlets in Saturn's rings are created by similar resonances with various moons. These resonances sculpt the ring's structure, creating the intricate patterns visible in detailed images. Orbital resonances demonstrate the long-term stability of gravitational systems. Once established, these resonances can persist indefinitely, requiring no energy input to maintain. Beyond Neptune's orbit lies the Kuiper belt, a region containing millions of icy bodies orbiting the Sun at distances from 30 to 50 astronomical units. This belt is similar to the asteroid belt, but far larger and more massive, containing objects composed primarily of frozen water, methane, and ammonia. The Kuiper belt is the source of short-period comets, bodies with orbital periods less than 200 years. When gravitational perturbations nudge Kuiper belt objects into orbits that bring them closer to the Sun, they become visible as comets, developing tails as solar heat vaporizes their icy surfaces. The Kuiper belt was predicted to exist decades before the first objects were discovered in 1992. Astronomers reasoned that the solar system should not simply end at Neptune, but should gradually fade out with a population of small, icy bodies. The discovery of the first Kuiper belt object confirmed this prediction and opened up a new region of the solar system for exploration. Thousands of Kuiper belt objects have been discovered since then, though this represents only a small fraction of the total population. Most Kuiper belt objects are too small and distant to be detected with current telescopes. The belt contains several dwarf planets, including Pluto, Makemake, and Haumea. These larger objects formed early in the solar system's history, when the outer regions contained more material. Most of this material was eventually ejected by gravitational interactions with Neptune, leaving behind the current population of Kuiper belt objects. The belt's structure shows evidence of Neptune's influence, with several populations of objects locked in orbital resonances with the giant planet. The classical Kuiper belt objects, those not in resonance with Neptune, orbit in the region from about 42 to 48 astronomical units. These objects have relatively circular orbits with low inclinations, suggesting they formed in place and have remained largely undisturbed since the solar system's formation. The scattered disk, a related population, consists of objects with highly elliptical and inclined orbits, likely scattered into their current orbits by gravitational interactions with Neptune. Some scattered disk objects have orbits that take them hundreds of astronomical units from the Sun, spending most of their time in the cold outer reaches of the solar system. The Kuiper belt gradually fades out beyond 50 astronomical units, though a few objects have been found at greater distances. The belt's outer edge may be defined by a yet undiscovered massive object, sometimes called Planet 9, whose gravity would have sculpted the outer solar system's structure. The search for such an object continues, with astronomers looking for subtle gravitational effects on the orbits of distant Kuiper belt objects. The Kuiper belt represents a reservoir of primitive material, largely unchanged since the solar system's formation 4.6 billion years ago. These objects preserve information about the composition and conditions of the early solar system, serving as frozen samples from the planet-forming era. The New Horizons spacecraft, after flying past Pluto in 2015, continued into the Kuiper belt and flew past the object Arrokoth in 2019. This flyby revealed a contact binary, two lobes gently joined together, providing direct evidence of how Kuiper belt objects formed through gentle collisions rather than violent impacts. The Kuiper belt will remain a focus of scientific interest for decades to come, as each discovered object provides new insights into the solar system's history and structure. The solar system moves through space in predictable patterns that have remained constant for billions of years. Each planet, moon, and celestial body follows its designated path, creating a cosmic choreography of remarkable stability. The facts presented here represent only a fraction of the solar system's wonders, but they share a common theme of order, consistency, and gentle processes operating on vast timescales. The magnetic fields that protect planets, the orbital resonances that stabilize moons, the geysers that erupt on schedule, and the rings that orbit with mathematical precision all demonstrate that the cosmos operates according to reliable physical laws. These processes continue whether observed or not, following patterns established billions of years ago. The solar system is not a place of chaos, but rather a carefully balanced system where gravity, momentum, and energy work together in harmony. Understanding these processes provides perspective on the human experience, placing our brief lives within a context of cosmic timescales and distances. The universe's vast age and size can be either overwhelming or comforting, depending on perspective. From one view, human concerns seem insignificant against the backdrop of billions of years and trillions of kilometers. From another view, the universe's orderliness and predictability provide reassurance that despite apparent chaos, fundamental patterns persist. The solar system will continue its quiet dance for billions of years into the future, with planets orbiting, moons circling, and comets returning on schedule. These facts are offered as an invitation to contemplation rather than excitement, to wonder rather than worry. The cosmos operates on its own schedule, unhurried and patient, and there is something deeply restful about understanding these vast, gentle processes. For those seeking calm, the solar system provides endless examples of stability and order. The same forces that have operated for billions of years will continue operating long after human civilization has passed. This continuity offers a form of peace, a reminder that beyond human concerns, the universe continues its ancient patterns. If these facts have provided a moment of calm, a brief respite from the urgency of daily life, then they have served their purpose. The solar system will be here tomorrow, following the same paths, operating according to the same laws, a constant presence in an ever-changing universe.